transmission? Okay, perfect. Yeah, then welcome everyone to the weekly colloquium of the Physics Institute of the UNAM in Cuernavaca in Mexico. Our guest today is Dr. Christopher Mankovich from the Caltech in the United States. So let me say some few words on the vitae of Dr. Mankovich. So he did his PhD in astronomy and astrophysics at the University of California in Santa Cruz. And yeah, since 2019, he is a postdoctoral research associate at the Division of Geological and Planetary Science at the California Institute of Technology in the United States. His research focuses on the formation of stars and planets. In particular, he is interested in the role played by fluid stability versus instability in these objects and the related question of how these objects naturally pulsate. Chris, thank you very much for joining us today, at least virtually. It would have been a pleasure to have been here in person, to host you here in person. And yeah, we're looking forward to your talk.
Great. Thank you so much, Thomas. Buenos dias, everyone. It's really my pleasure to be visiting, virtually anyway. And I'm excited to tell you about some of these cool results that we've been finding at Saturn lately. So I think I'll just dive right into the main event. Gas giant planets are really fascinating things to study in astronomy, in part because they dominate the mass budgets of planetary systems. They contain kind of primordial building blocks, we think, of the solar systems that they formed in. And so learning about their structure and their composition, the way that they're put together, can really tell us a lot about the full story of our solar system and for the planetary systems in general, of which there are many, many, many studyable systems in the galaxy. So a big question we want to answer for giant planets is what's the nature of their formation process, and the related question of what's the nature of their cores. And the prevailing theory for how giant planets get assembled is the theory of core nucleated accretion and the related kind of theory of pebble accretion. This is a picture from kind of a classical style core accretion simulation that can build a giant planet, like say a Jupiter. And the basic story is that there are distinct phases. There's an initial phase in which planetesimals are accreting into kind of a solid core. At some point, that growing solid core is able to begin to trap gas from the nebula. And when a planet has roughly an equal part of gas mass and heavy element mass, it can trigger a runaway accretion, some say a dynamical accretion, of gas from the nebula, and then accrete most of its mass in the form of a gaseous envelope. And so this is sort of the standard picture for the accretion of, say, Jupiter. And this indeed is a simulation over time that shows a planet accreting first its core, then begins to accrete some gas before a runaway accretion event in which the planet gains most of its mass and ends up at 315 or so Earth masses. This idea has been around for a long time, and it has a major testable prediction, which is that gas giants have dense cores. So the existence and the mass of cores in our local gas giants, Jupiter and Saturn, was kind of a main mission objective for the Juno mission to Jupiter and the Cassini mission to Saturn. And so you might have heard about this being sort of one of the main points of these missions. Juno and Jupiter is a huge one. And the way that they're supposed to answer these questions for us is with gravity field experiments. And that might not mean anything to you, or it might. So I'll talk a little bit about what does that really mean when we say that Juno and Cassini can tell us about the cores of these planets. Well, we have these spacecraft that can conveniently be sent to these gas giants, which is part of the reason why the solar system is an incredibly convenient place to be answering these questions, because we can actually build spacecraft and send them to the planets. And it's often said that the gravity field measurements that these spacecraft do is a free measurement, in the sense that it doesn't require a dedicated instrument. What it actually is just making use of the radio downlink that these spacecraft have to Earth anyway for navigation purposes in order to track radial velocities as a function of time. And so the way that these spacecrafts orbit is a function of the gravity fields of the planet themselves. And so it's really just determining the orbits of these spacecraft that can tell us the gravity fields of the planets. The reason that's useful for understanding the interior physics is because the potential outside of a planet can be kind of thought of as a multipole expansion. These planets are not point sources of mass because they are distorted by their rotation. And as a result, there is actually a long series of non-spherical terms in the potential. This is leaving out influence from satellites and other bodies in the solar system for the moment. But the field of just one of these oblate planets can be written as this multipole expansion. And you'll notice that there are some familiar items in here. It depends on the mass of the planet. It depends on your distance from the planet and the planet's radius, as well as these Legendre polynomials. That's the kind of nature of the expansion. And inside this expansion are these coefficients, these J2n. And these are really the prizes when it comes to trying to understand the interior of the planet. These gravity coefficients, J2n, I might also call them gravity harmonics, are essentially just integrals of the mass distribution over the oblate planet. So J2n is ultimately measured because the gravitational potential is measured. And inside of this integral that's over the volume of the planet is the density. And so when you measure the J2n, you are encoding the full mass distribution over the non-spherical planet. And this is a function, of course, of the composition, the temperature, the shape, and the rotation, and more specifically, the spatial distribution of all those things. The kind of unfortunate part about using these types of measurements to back out the density distribution of the planet is that you are integrating over the volume of the planet. So these are integral quantities. And as a result, they are only sort of, each one is a scalar that tells you some integral. It doesn't necessarily uniquely tell you the distribution of those quantities. This is a plot that summarizes the contribution functions to these J2n, starting from 0, 2, 4, 6, 8. So J2, the contribution function over, say, Saturn's radius to J2 is given by this blue curve, where the maximum value sort of tells you the key region to which that quantity is sensitive. And you can see that in general, all of these gravity harmonics are weighted heavily toward the planetary surface. And so they intrinsically carry kind of weak information about the deepest interior parts of the planet. C0 in this case is just the contribution function to the total mass, which we know anyway, so it's not helpful. So there's kind of an inherent disadvantage in using these quantities to study the deepest parts of the interior. With that in mind, I'll give you kind of a picture of theorists' sort of best guess for the structure of Jupiter before Juno gravity started coming down around the time that I was a PhD student. So this is just one particular model for Jupiter's interior structure from Hubbard and Militzer. And this plot is showing density as a function of radius in the planet normalized to the total radius. And this is a model that features a classical kind of compact core. So you'll notice there are pretty distinct densities describing the envelope, which is dominated by hydrogen, and the core, which is just assumed to be a core of pure heavy elements like silicates and water ice. The cartoon here shows you kind of a general summary of the compositional structure that's assumed in a classical model like this. There's an envelope of molecular hydrogen. There's an inner envelope of metallic hydrogen. And the reason for this is really that for the temperatures typical of the giant planets, as a function of increasing pressure, as you move into the planet, you eventually start to sort of pressure ionize the hydrogen, and it takes the form of a metallic fluid. And so there's a major difference in electrical conductivity between these two layers, which is why they're thought of as sort of distinct. There's also something else going on, which is indicated sort of here in this layer, and also in the fact the outer envelope is said to be helium depleted, while the inner region is helium rich. And what this is a helium rain layer. So something related to the fact that hydrogen becomes a metallic fluid as you increase the pressure is the fact that the helium, which remains neutral, tends to come out of solution. And so helium and fluid metallic hydrogen are not perfectly miscible. And it turns out that Jupiter is so cold that this phase separation between hydrogen and helium is happening. And there's a lot of evidence for that, both from kind of first principles physics, also from an in situ measurement of the helium abundance in Jupiter's atmosphere that was given by the Galileo entry probe. And recently, maybe some have seen a Nature paper reporting an actual laboratory detection of this hydrogen helium immiscibility for the first time, which is a major step forward because it's a piece of concrete evidence for this idea that has been around for many decades and applied to Jupiter. So anyway, this was sort of published as the best guess for Jupiter's interior structure prior to Juno. Now, with the benefit of Juno data, our ideas for Jupiter's interior structure are starting to move a little bit because of what the data are requiring. This is a plot from Sean Wall's 2017 paper that is basically fitting similar data, although now with the benefit of very precise gravity harmonics for Jupiter that extend for several degrees. And so there's J2 all the way up to J10 in terms of these even coefficients that are most valuable for constraining the deep interior. So there are models with classical compact cores, but what it looks like is that diffuse cores, as opposed to these really compact, pure heavy element cores, tend to be helpful for fitting the gravity spectrum, especially Jupiter's J4, which is rather hard to fit with the models that I was showing in the previous slide. And this can take the form of, say, just a model where the same amount of heavy element mass that was previously in a compact core is just blurred out to, say, 40 or 50% of the planet's radius, or it could be a gradual distribution of that same amount of composition. It's really not clear from the gravity field because, again, it's intrinsically an integral quantity that does not tell you about the distribution specifically. So now we're starting to have a picture for Jupiter's interior, maybe, where there is not such a neat division between a compact heavy element core and the envelope that's dominated by hydrogen. And there might be a few reasons for that. Metallicity gradients might just be naturally built up during core and pebble accretion. In part, that's just because there are not really these clean episodes of heavy element accretion followed by an episode of gas accretion. In reality, there's kind of a continuum of accretion rates that vary between pure rock and pure gas. So given that gas can really accrete at the same time as heavy elements, you can naturally build up bottom heavy composition gradients. Whether or not those gradients that are built up in accretion simulations can actually survive for billions of years of evolution is really up for debate, because the cooling of these planets tends to drive convection. That convection can sort of erase or erode these composition gradients. And so it's not clear whether those primordial cores can kind of survive intact at the solar age, although it's likely that at least the deepest parts of them do. There's a separate issue at play here, which is just the fundamental solubility of rocky and icy material in liquid metallic hydrogen. So there's been a kind of series of works in high pressure first principles physics that show that water ice and even silicates can just be dissolved by fluid metallic hydrogen. And so even if you formed with a kind of discrete core, like in the classical core accretion picture, that can still probably mix with the overlying fluid over time and potentially be mixed into a diffuse structure. And the final possibility that I'll mention is the possibility of giant impacts. So after a core accretion kind of formation of a planet, it's still possible that that planet experiences a huge impact, which can tend to give you a diffuse core if the conditions are kind of just right. And that was in this really cool work by Liu et al. In Nature. I will say that seems a little bit more remote than the other possibilities in my mind, just because the particular simulation that showed that you can get a very diffuse core like this kind of structure for Jupiter happens to be a very massive and a very kind of fortuitous impact in the sense that it has to be dead on. And it's not clear whether, given kind of a realistic distribution of impact distances, whether this can actually take place. So anyway, Juno is sort of hinting at this kind of diffuse core structure in Jupiter, but it's really not clear yet whether one is strictly required. It kind of depends on who you ask. And one of the major uncertainties in giant planet interiors is still the equation of state. Even the equation of state for hydrogen, unlike stars, it's really not well known in the conditions of these giant planet interiors. And it's intrinsically really hard to study experimentally. And so as a result, if you kind of use different equation of state assumptions building your model, you might get different answers. And I think it's too soon to say definitively whether this diffuse core is necessary in Jupiter. But more gravity data may help to answer that question. And the Juno mission is ongoing, so stay tuned. So how does all this kind of play out for Saturn? Like Juno, there is a phase of Cassini's mission that was spent in really close orbits around Saturn to measure its gravity field. And so what have we learned? And the answer is it's a lot harder to answer this question for Saturn. And the main reason for that is because the interpretation of Saturn's gravity field is kind of confounded by this issue of very deep zonal winds. One of the huge results from the Juno mission at Juno, and then also from the grand finale of the Cassini mission at Saturn, was the result that the zonal wind patterns that you can see on the surface of the planet, they're plotted here in these diagrams, actually just extend quite deep into these planets' interiors, which is not something that was at all clear before these spacecraft actually started delivering these data. This is a plot that shows the spectrum of even gravitational harmonics for Jupiter in green and then Saturn in red. And the expectation was more or less the expectation for uniformly rotating models, which are shown in kind of the smaller markers here. And what was found instead is that the higher degree gravity coefficients were really enhanced compared to the rigid model. And this is not something you can really explain with an alternative structure for the planet. It's really only something that you can explain by appealing to the fact that velocities in the actual fluid extend quite deep into the planet relative to the rigidly rotating model. And as a result, these gravity coefficients can kind of be enhanced. If you think about it, it's sort of an effect where the additional rotation from, say, an eastward jet near the equator kind of amounts to a little bit of centrifugal lift. And so effectively, the kind of mass that the spacecraft is feeling is a bit different because of the velocity. So you'll notice that the effect on this diagram for Jupiter is kind of tiny compared to the effect for Saturn, where these higher coefficients are really, really strongly affected by the differential rotation. You can sort of back out a family of profiles that are allowable for the wind amplitude as a function of depth. And that's what's shown here for Saturn above and Jupiter below. And it's not uniquely determined, but scientists like Yohai Caspi and Eli Galanti are able to make really informed guesses and show that the gravity actually constrains the allowable profiles quite well. And they penetrate to similar depths, it seems. This sort of differentially rotating part of these planets' exteriors penetrates to similar depths in terms of pressure. But because these planets have different masses, that really corresponds to sort of different depths in the planet. So in Jupiter, this extends to something like 3,500 kilometers, say, very roughly. And in Saturn, these winds penetrate to maybe 9,000 kilometers. When you account for the fact that Saturn is only 1/3 the mass of Jupiter, you realize that these differential flows are actually influencing a significant fraction of Saturn's mass. And this is part of the reason that these gravity harmonics are really influenced largely by that differential rotation. And so an outcome of this is that we're really not able to say anything quite as definitive about Saturn's interior mass distribution, because the J's, certainly J12, J10, J8, even J6, and even J4, when you look at it, are pretty significantly affected by the differential rotation. And so it's a lot harder to say anything about the contribution, the separate contribution from the interior density distribution. So it's a bit muddier. And unfortunately, this really leaves Saturn's core as an unsolved problem from the perspective of Cassini gravity. So is there another way we can study this? And you've probably already guessed that I'm here to tell you yes, and how. So that brings us to the promise of seismology. Seismology would be an independent way to study this planet. We know that seismology is tremendously powerful in a number of different objects. Terrestrial seismology is obviously the birthplace of seismology. And you can study the Earth using its normal modes, but a lot of the information has come from not using normal modes, but studying instead just body waves that propagate following an earthquake. So this is kind of a cartoon that shows how the two main families of body waves, pressure waves and shear waves, can travel in the Earth's interior following an earthquake. And so there are a number of things you can learn about the Earth. Just one example among the greatest hits is Inga Lehmann's determination that the Earth's inner core is actually solid. So in the kind of previous picture where the entire Earth's core were liquid, you have this massive shear wave shadow zone, because a fluid core cannot support shear waves. And so they evanesce in this liquid core, and most of the planet on the far side of the epicenter of the earthquake would have no detectable shear waves. Likewise, P waves are kind of diffracted differently in the liquid part of the core and the solid part of the core. And what became clear is that some some of these P waves were observable on the exact opposite end of the Earth than the epicenter, which kind of indicated that part of this inner core needed to be solid. And that's just one of many kind of stories that terrestrial seismology had to tell about the interior structure of the Earth. Helioseismology was kind of a total game changer for our understanding of solar physics. The sun turns out to oscillate with what are mostly P modes, which are trapped sound waves that are excited by convection in the outer regions of the sun. If you've heard of the solar 5-minute oscillation, that's an example of solar P mode oscillations. And this has told us a number of things about the sun and its external structure, including the finding that rotation varies as a function of latitude in the solar convection zone, and that this differential rotation kind of disappears once you reach around 70% of the sun's radius, which is thought to be the lower part of the solar convection zone. That's referred to as the tachycline, and it's kind of thought to be the seat of the sun's dynamo that generates its magnetic field. And then below that is a radiative zone that appears to be rotating kind of rigidly. So this was all information that was only possible because of helioseismology. Asteroseismology is a similar method that applies normal modes to understand the interiors of other stars beyond our sun. And just to give just one example, there are many classes of pulsating stars, but red giant oscillations have been studied using photometry from missions like Corot and Kepler, now TESS. And red giants are really fascinating because they exhibit not just P modes like the sun, but mixtures of P modes and G modes that live in the core. G modes are trapped internal gravity waves that are restored by buoyancy. And there have been a couple huge results that came out of this kind of field. One of them is this nature result, gravity modes as a way to distinguish between hydrogen and helium burning red giant stars. This is kind of fascinating because on the red giant branch, in terms of the location on the Hertzsprung-Russell diagram, there's no way to tell which red giants are ascending the red giant branch versus those that are sitting on the red clump burning helium in their cores. But this mixed mode seismology made it possible to kind of disentangle those two families because they have different signatures in their pulsations, because one of them has a convective core in part of this helium core that's burning helium. Another huge result is just the measurement of core rotation. These same gravity modes were able to deliver the rotation rate of the interior tiny helium core at the center of these red giants that are pulsating. And it revealed the fact that the core is rotating faster than the envelope of these stars by at least a factor of 10, which was not known at all. Results like this make me say it's arguable that we understand the interiors of red giant stars better than we understand the interior of Jupiter or Saturn, because this seismology is so readily available. Now there are hundreds of thousands of oscillating red giants in tests, and it's going to be really fascinating to see what we can learn, especially because these are now distributed over the full sky, as opposed to the small field that Kepler was staring at. And I'd be remiss if I didn't mention Martian seismology, which is, there's an incredible trio of papers that came out just about a month ago, delivering seismic results from the Mars InSight seismometer. This is a cartoon from just one of those papers that has results about the Martian core. And this finding was kind of driven by Mars quakes that were picked up, these shear waves that were picked up after having reflected off of the core boundary. And so the detection of these Mars quakes made it possible, in part through an analysis of their polarization, made it possible to determine the radius of Mars's core. And so this is an incredible new detection that's happened in planetary seismology. And it's really exciting to see Mars InSight kind of delivering this kind of stuff. So where does that leave us with giant planets? Can we do giant planet seismology? And so far the answer is not in a way that's useful. This is a result from Nice Observatory. This is Golm et al. 2011, showing a power spectrum for Jupiter that was obtained from radial velocity maps of Jupiter's surface. So an oscillating planet should show radial velocities on its surface, and measuring their frequencies could tell us about the interior structure. This power spectrum shows a bunch of excess power that it seems like is in a plausible place for Jupiter's P modes, with amplitudes at the surface of 10 to 50 centimeters per second. There's a secondary bump over here that it's unclear what the origin of that is. But this might be a detection of Jupiter P modes. Unfortunately, it's certainly not the level yet where individual modes can actually be picked out, which is going to have to happen before these can be useful for constraining the interior structure of Jupiter. So I think this is a really promising field that we should all be keeping our eyes on in the coming years. So at Saturn, we really have a unique probe in the form of ring seismology or chronoseismology. First, I want to just say that ring waves throughout Saturn's rings are really quite common, and they've been known to exist for a long time as a result of satellite orbits. So if you look at a photograph like this, these look like almost radial patterns. They look almost axisymmetric, but what these actually are spiral waves that are wrapping all the way around Saturn inside the rings. These waves can take one of two flavors. These are all waves that are sort of propagating away from Saturn. These are spiral density waves, which are just created at what are known as Lindblad resonances with eccentric moon orbits. And all that means is that there is some perturbing frequency from an orbiting moon that is giving gravitational pushes and pulls to ring orbits on timescales that are commensurate with like the local response frequency of the ring orbit. And so there's some resonance condition, and satellites can create a huge family of resonances. Each satellite can. And so the rings are just full of these things. There's also a separate flavor, which are not density waves, but bending waves. Those are actual vertical excursions in and out of the ring plane. And an inclined moon orbit can force that kind of wave in the rings too. And just to kind of paint a picture, those spiral density waves physically are really analogous to spiral arms in galaxies that are driven by central bars that are rotating. Those bars have resonances inside the galaxy that can give you spiral arms of stars. Likewise, bending waves can be seen in warped galaxies, although these might be more like chance encounters with a single gravitational perturber than any resonant forcing from inside the galaxy. So around the Voyager era, 80s into the 90s, there was a question that arose from my now colleague at Caltech, Dave Stevenson. Are Saturn's rings a seismograph for planetary oscillations? So like I mentioned, the rings are full of satellite resonances. This is one example of a density wave that is out in the A ring. This signature of decreasing wavelength is kind of the direction of propagation as you move away from the resonance. So this is a satellite resonance with some satellite propagating outward in the rings. This is the signature of a forcing frequency that's slower than the ring orbital frequency. In the C ring, there are a bunch of waves that actually didn't have any clear interpretation when they were initially observed in Voyager radio occultations. So this is a radio downlink that is going through the rings toward the Earth to measure density variations in the rings. These density waves are propagating in the opposite direction from this density wave, which is the signature of a forcing frequency that is greater than the ring orbital frequency, which is sort of a telltale sign that the origin for these ring waves is within the rings, and indeed from Saturn itself. And Mark Marley and Carolyn Porco are two people who took this idea quite seriously and really worked out the mechanism by which Saturn can drive potentially observable ring waves. They are the first to put their finger on the importance of F modes inside Saturn. And F modes are fundamental modes of oscillation. They're essentially sort of gravity waves that are trapped on the surface of the planet. And the key thing about F modes is that they have no nodes as a function of radius inside Saturn. So if you look at the eigenfunction of one of these normal modes of oscillation as a function of radius in the planet, the perturbation is coherent as a function of radius at any given phase. So you should imagine this as an oscillation mode. So as a function of time, this thing will be swinging about zero, but at any single phase, the perturbation is coherent across the full radius. And what that means is that it can have a strong influence on external gravity, because from outside the planet, you actually see a density and gravity perturbation as a function of time. These oscillations are understood in terms of spherical harmonics, which is why I put a couple of pictures on here to show you the types of modes that we're talking about, but I'll talk about that in more detail in just a minute. These F modes in Saturn have periods of 2 hours or faster. Marley and Porco showed that around 1 meter surface displacement on Saturn is sufficient to give you an observable density wave. And most of these resonances with Saturn F modes were predicted to land here in the C ring, including specific locations where those Rosen et al. Waves that I was showing on the previous slide showed kind of mystery waves in Voyager data. just to give you kind of a zoomed out view of various modes that could be at play inside Saturn and what those F modes mean. Here is frequency in units of Saturn's dynamical frequency, which is really just a function of its mean density. In those units, F modes have frequencies of about 1. And they can increase from there as you look at different angular degrees, but they start at around between 1 and 2 times Saturn's dynamical frequency. Up here are P modes. So I mentioned P modes in the context of the sun and red giant stars. P modes have higher frequencies. They have overtones. So they are overtones, and so they have nodes as a function of radius in the planet. So they generally give you weaker gravity perturbations. And in any case, their frequencies are too high to be resonating in the rings. And so P modes, we are not sensitive to by studying the rings. Down here is Saturn's rotation frequency. It's about 0.4 of breakup. So Saturn is actually quite a rapid rotator. It's part of why it's so, that is the reason that it's so oblate. And associated with the rotation are modes whose restoring force is the Coriolis force. And those go up to about twice the rotation frequency. And so below this point, you should expect lots of inertial modes. These are likely weak for perturbing the external gravity field and they have low frequencies. So F modes are kind of lucky in that they're both strong and they, in terms of frequency, fall in the sweet spot where they're observable using the rings. And if you have an interior model that has a positive buoyancy frequency N in the planet, you're also going to admit G modes. And this is really unknown, at least before we have ring seismology. And I'm trying to foreshadow a bit of where we're going with this. So anyway, we have a huge family of modes that are possible. Their angular structures can be understood in terms of spherical harmonics, which you might know from, say, quantum mechanics. And here L is running down, that's angular degree, and M is running left to right. A large number of these can be discarded for the purposes of ring seismology. For instance, these are zonal modes. They're totally axisymmetric, and so they cannot give you a response in the rings because there is no non-axisymmetry to them. These modes are retrograde, and that turns out to not be able to give you any resonances with prograde ring orbits. That leaves only prograde modes, and these are the modes that are interesting from the perspective of ring seismology. Among these prograde modes, there are sort of 2 flavors of geometries as a function of their symmetry about the equator. And modes that are symmetric about the equator can drive density waves at Lindblad resonances. Those are most of the detections that we turn out to make for Saturn. And bending waves are modes that are anti-symmetric about the equator, and those can drive those vertical oscillations and give us bending waves. And this is just to remind me to say that these cartoons show 2-armed spirals. And there's a really straightforward mapping between the structure of the wave that you get and the structure of the perturbing planet mode. So these are both 2-armed spirals. And so these would be caused by M equals 2 perturbations inside the planet. That is 2-fold azimuthally symmetric patterns. So with that out of the way, I can talk about kind of the main observational results that came out of some really talented people analyzing stellar occultations using Cassini data. This is an example of just one spiral density wave that turns out to be because of a Saturn normal mode. And this is work initially by Matt Hedman and Phil Nicholson, as well as Richard French. So several papers have come out over the years right up until just now. They're continuing to turn out these waves. And the ability to observe these waves at multiple phases, because the orbits around Saturn was such a long project over more than a decade, really lets these waves be characterized really well in terms of their frequencies and also their azimuthal wave numbers M. And so that leads us to our new window into Saturn. And this is kind of a summary of all of those data that tell us about Saturn's interior. Here we're plotting all of those detections in these field symbols, and we're showing them on a diagram of azimuthal pattern number M, so how azimuthally symmetric the pattern is, as a function of radius from Saturn's center, which is really just a proxy for frequency since the orbital frequency decreases away from Saturn. The sort of grayed out region here on the left is the D ring, which is a really faint ring where these resonances would not be observable because there's kind of now a large response from the ring orbits. The rest of these are the C ring, and this is where we have all these excellent detections. And here we're comparing them with a simple Saturn model that just assumes a conventional layered structure, so it has a solid core, and therefore predicts only F modes. Now you can immediately see, well, so there's a lot of detail in these angular kind of labels that I've attached, but you don't have to worry about that for right now. But just to orient you a little bit, I'll point out a couple of the modes. This main sequence over here are the sectoral modes. They're these modes where L equals M, and they give you this kind of beach ball structure. So this is the 4-4 sectoral mode. As you move up this sequence, the modes look more like this. And if you start to vary the value of L plus M, then you can get more latitudinal structure. So over here is a mode where M is equal to L plus 8, and it has this insane amount of structure on its surface. And that is a mode that has been detected. Just to give you an idea of kind of the diversity of angular structures that we're sensitive to in Saturn now. There are kind of two overall classes in this diagram. You can see there are predictions where the model does a good job. Sorry, there are detections where the model does a good job. And these are evidently just F modes inside Saturn, just like I've described so far. And these are really useful for constraining interior rotation inside Saturn, but they're mostly located near the surface. And so they don't tell us a lot about the deep interior. The other family is down here, where this simple model clearly does a terrible job of explaining all of these detections. And so what is going on there is the main thing that I want to talk about today. And the kind of answer is that Saturn hosts G modes. These detections we think are possible because part of Saturn's interior is stably stratified by a composition gradient. And that's an idea that was first laid out by my now collaborator, Jim Fuller, now professor at Caltech, back in 2014. And he argued, when only a subset of these data were available, that Saturn featured some stable stratification in its interior, probably associated with the boundary of the solid core that could support G modes. And so Saturn's interior hosts not just an F mode cavity, but also a G mode cavity deeper down. And again, in Saturn, this can only be provided by a composition gradient, because these interiors are so opaque that by default, they're fully convective unless there's something else going on. And in reality, it's an oversimplification to say these are all G modes. In reality, they're all mixtures of F and G modes. They're not so easily organized into distinct flavors in all cases. There are also two kinds of things going on in these detections at n equals 2 and n equals 3. Here you have examples of fine multiplicity that we think we can understand as being induced by Saturn's rapid rotation. This is a main result from my collaborator Janos Dewberry's work on understanding this fine multiplicity. And this is just an example of 3 modes that are produced in a model that has a stable stratification in the interior, where the deep structure of the normal mode actually is that of a G mode, or in this case, what's called a rosette mode, which has a more complicated structure. These are all modes that are only possible because of the buoyancy of the interior, but they're all mixed with Saturn F modes. And so near Saturn's surface, they look more like F modes. They have these strong gravitational perturbations near the surface in these azimuthal, in these meridional slices. And so, for instance, this n equals 3 triplet of very closely spaced detections can probably be explained just by appealing to mixed modes induced by Saturn's rapid rotation. And the rotation really helps these modes mix together in a way that would not be possible at all on a non-rotating planet. The other thing that's going on here is this coarse multiplicity that's observed at n equals 2. And that is really what's driving the main results that I'm here to talk about today. And we think that just results from consecutive G mode orders inside the planet. So to make a long story short, we think that this coarse multiplicity observed at n equals 2 is just the result of the fact that we are seeing not just the F mode, but also G modes of consecutive order. And so we labeled F, G1, G2, G3. Note that even the F mode is G mode-like deep down. It has oscillatory character. So it's not even a pure F mode in the sense that I told you about earlier. It's really sort of F mode-like, sort of G mode-like because of the stably stratified nature of the interior. Likewise, all of these G modes are kind of F mode-like at the surface, whereas a pure G mode would really just be entirely confined in the core and have no amplitude at the surface. So it happens to be that for Saturn, these F modes and G modes are really overlapping in a way that they are all observable, which is really valuable for making use of these frequencies to understand the deepest interior. And here we're moving on to the main results, our finding of a diffuse core in Saturn. When we actually build Saturn models with realistic equations of state and consider different composition profiles, we can ask ourselves what's necessary to reproduce these m equals 2 ring seismology constraints. And so here what we're doing is looking at a family of interior models with a bunch of different candidate heavy element distributions. This is just one family that you could consider. So this is mass fraction of heavy elements as a function of radius in the planet. And this is the buoyancy frequency in units of the dynamical frequency as a function of radius in the planet that follows directly from this composition profile. And the kind of model in this family that you choose really has important observational effects in the rings. So here we're showing the predicted mode frequencies for m equals 2 in the ring plane, where here in this diagram, we have increasing mode frequency to the right, increasing distance from Saturn going to the left. And there are 4 m equals 2 detections. I mentioned that this fine splitting is the result of this rotation effect that we're not exploring here with these interior models. So we think that's understood by some other mechanism. So the task here is really to reproduce this overall trio of frequencies. And you can see that there's this one frequency at extremely high. There's this one mode detection at extremely high frequency, this wave that's labeled 7644. And this is kind of the smoking gun that really points to a diffuse core in Saturn, because it's a very high frequency that can only really be explained by another L equals M equals 2 G mode. And its frequency is simply too high for any model that does not have a diffuse core. So models that have a very steep transition between a core and an envelope, and therefore have a really peaky profile of the buoyancy frequency, predict an extremely large value for the frequency of this G mode that is way off the plot, and so simply can't explain the observation. And try as you might, there's kind of no way to massage the interior model, even when you consider more complicated interior models, to produce a frequency at this radius. And so this is what drove our main kind of pursuit of the extended core inside Saturn. We pursued this in more detail and kind of systematically by using joint fits to the seismology and gravity field. And that's done with an interior model that has a few free parameters. And then we fit that to the set of gravity harmonics and m equals 2 seismology constraints using Markov chain Monte Carlo. And our main findings are this extended stable stratification, where the interior is stably stratified and the exterior is convective. Notice that the details depend a little bit on your parameterization, the kind of shape of the composition profiles that you assume. Here we're comparing our main models to models that have a composition profile that's forced to be smooth. You can see they have slightly different predictions for the extent of this stable stratification. Only a few parameters really matter here. There's that extent of the stable stratification, the metallicities outside and inside this gradient region, and also the deep helium fraction. I'm not talking a great deal about helium rain today, but our models do also include a helium gradient that coincides with the heavy element gradient. We find that light species, hydrogen and helium, are probably mixed all the way down inside Saturn. And that gives you really modest central densities that are actually extremely well constrained as a function of radius, just by the joint application of gravity and ring seismology. And those profiles are well constrained, but this kind of leads to a bit of an ambiguity in how to talk about them, just because we're really taught that the key question about these planets is what is the mass of their core, but the core is actually kind of an ill-defined concept now that we have a diffuse core. This diagram says that half of Saturn's heavy elements are within a third of Saturn's total radius. The total heavy element content is just similar to existing models because that's actually mostly dictated by the mean radius, by the total radius of the planet anyway. If instead we equate the core with the stably stratified region that includes a gradient of composition that might have been built by the formation process, then we're finding whopping core masses of 62 to say 78 Earth masses, radii of 0.6 to 0.75 RS Saturn radii. So it really just depends on how you define your terms when it comes to what we found for Saturn's core. The important part is that it's very extended. I'm going to skip this for time. One thing that would be really nice is to learn about heat transport inside Saturn. There's this decades-old problem in understanding Saturn's interior structure, which is that fully convective, and so nearly adiabatic interior models, if you make an evolutionary model like that, then you seriously underestimate Saturn's present-day luminosity. So this black curve is one of those models. It doesn't look that bad on this plot, which is log temperature, but in terms of luminosity, you would be underestimating Saturn's current day luminosity by something like 50% if you have an adiabatic model. And really cool work from LeConte and Chabrier showed that if the model were not fully convective, but had a fraction of its interior undergoing layered convection as a result of composition gradients, then you could actually find a large family of solutions that can explain Saturn's present-day luminosity. And these are just a natural result of composition gradients in principle, although the efficiency is not really well understood a priori. And so can we probe the temperature profile directly to learn about whether this is operating in Saturn definitively? It certainly aligns well with our finding of the diffuse core and a massive composition gradient, but can we say so for sure? And the answer, unfortunately, is no. We pursued a bunch of super adiabatic models that allow this composition gradient to be undergoing some other form of mixing, like double diffusive convection, that would give you super adiabatic temperature profiles. But the answer is that it really doesn't influence the buoyancy very much, and therefore doesn't really show up in the G mode frequencies very much. And the reason for that is simply that in the buoyancy frequency, the composition term from a gradient like this just far outweighs the thermal term for any plausible temperature profile. So we're not able to put our finger on the temperature profile inside Saturn based on these measurements, and that's going to be a fundamental limitation of the ring seismology. The other important thing that we've been able to learn about Saturn is a result of these modes that are at higher M values and tell us more about the rotation of Saturn. And in 2019, we were able to use rigidly rotating models for Saturn to put a new constraint on Saturn's deep rotation rate. And this is something that's kind of been notoriously hard to measure because Saturn has a quirky magnetic field that does not easily give away the planet's rotation rate. This rotation rate for the interior is significantly faster than any of the magnetospheric rotation rates, which kind of added to the body of evidence that Saturn's magnetic field rotation is not really tracking the interior rotation very well. Now there are many more measurements than were available in 2019, roughly double actually. And there's this additional new evidence from gravity science that Saturn's winds go deep. And so together with Janos Dewberry, I've been looking into how these differential flows play out for Saturn. Here again are those results that Janos found when he was studying differential rotation and this fine splitting. These same modes that I was showing can be used to show that deep winds can really enhance the mixing between the F and G or rosette modes. And this is a really cool paper that Janos wrote that I suggest you check out. We're finding in ongoing work that the F mode frequencies, with this nice tool that Janos Dewberry developed to calculate these mode frequencies more accurately than was possible before, because it accounts for rotation in a complete way, are really confirming the finding from gravity science that the zonal winds inside Saturn are quite deep. So if now we're plotting mode frequency residuals, not just for one M value, but for a large swath of M values, and the residuals don't look great for a rigid body model. And if you increase the depth of zonal winds inside Saturn just by extending them inward on cylinders, which is a theoretical prediction for how these winds play out inside of a convective fluid, we find that you definitely need a deep differential flow in order to explain the F mode frequencies. It kind of just continues to get better as we increase the wind depth. And part of that is just because at some point, the depth of the winds gets below where these modes have most of their amplitude. And so they're actually pretty unable to set an upper limit by themselves on the wind depth. But when you pair that with the fact that they're also sensitive to the bulk rotation, you can actually kind of constrain both at the same time. So these F modes are sensitive to background spin, mostly because there's a Doppler shift that takes you from the planet frame into the ring frame where the resonances actually are detected. And that's what made our 2019 detection of this constraint on the rotation rate possible. Now we're finding that our optimal rotation rate for this particular interior model might be 1 minute slower than that. And if we do everything sort of all at once and fit the seismology and gravity field using interior models that actually include a differential rotation profile, we're starting to get joint information on the wind depth and Saturn rotation period. So the ring seismology through these F mode frequencies is a really new and powerful tool to study the rotation profile because it's not just sensitive to the depth, but also very sensitive to the background rigidly rotating deep interior of the planet. And this is preliminary, but we're looking forward to getting these results out there soon. I'll wrap up by presenting a lot of open questions. Our model for Saturn's deep interior doesn't perfectly fit the F mode frequencies, or sorry, these mixed mode frequencies at low M, which you might have noticed on a previous plot. These these red lines here are really underpredicted by the model, which puts a cloud of kind of resonances down here. And so this imperfect fit points to the fact that our model is probably incomplete. It might have a slightly different shape to the composition distribution. And it's important to remember that we are studying Saturn using some of the longest radial wavelength modes that the planet has. And because of these long wavelengths, these modes inherently can't feel much shorter length scale changes to the buoyancy. And so what that means is that these results really leave room for somewhat different shapes of the heavy element distribution, the helium distribution, including potentially decoupled heavy element and helium gradients in the planet. That remains a very real possibility, although this diffuse core probably cannot go away. The G-mode cavity can also take the form of layered double diffusive convection, which is actually many convective layers separated by diffusive stable interfaces, but it's a large number of them. And so these G and F modes really don't care about the fact that those layers, that the stable region might be layered because they're only sampling it over long length scales. So a layered double diffusive structure remains a very real possibility for Saturn. And so that might be the way that the diffuse core is transmitting most of its heat outward in the planet. One major thing is that we also have no satisfying answer for Saturn's peculiar magnetic field. You might know that Saturn's magnetic field externally appears almost perfectly axisymmetric, which is kind of a surprise given that it's thought to be generated by a dynamo action somewhere inside the electrically conductive part of Saturn. An axisymmetric dynamo can't exist from kind of fundamental arguments. And so it's usually thought that there's a dynamo somewhere in the planet that has a stable layer on top of it that filters out non-axisymmetric components of the magnetic field because of differential flows. And the result is that at the surface, you can observe a totally azimuthally symmetric magnetic field, which is what's observed. So the model that we put forward, it sort of doesn't have an explanation for that. We have a stably stratified dilute core. If you go too far out in the planet, you're no longer electrically conductive, and so no dynamo action is possible. So this model that we put forward might only leave kind of a thin region where it's no longer convectively stable. So it's undergoing convection, but the electrical conductivity is still high enough that some dynamo action is possible. This kind of shell dynamo might not be able to explain an external magnetic field that is axisymmetric or dominated by the dipole component, which Saturn's magnetic field is, or is constant in time, which Saturn's magnetic field appears to be. There's a recent paper from Jan and Stanley that has nice dynamo simulations that appeal to a pretty broad stable region that they ascribe to helium rain as the sort of filtering region between the dynamo and the surface. And this can nicely explain those properties of the magnetic field, principally its axisymmetry. But this model cannot provide explanations for the data in the ring seismology or the gravity field. And so reality might need to be a hybrid of the two, where we have a dilute core and some dynamo generation region deep in the planet, but then a second stable region because of the helium gradient. And so pursuit of a model like this is a really important avenue for the work that we are doing now. So a big question is the Z gradient primordial? I'll wrap up in just a minute. And it's still unclear. This is kind of what the heavy element distribution looks like as a function of mass in one family of our models. These are simulations of accretion and evolution for Jupiter. And this is a paper that argues that it might be hard to get as diffuse a core for Jupiter as seems to be necessary based on Jupiter's gravity field. It's unclear whether for Saturn you could produce a structure like this just based on the accretion process and the cooling that follows. And like I mentioned earlier, part of the problem is that the cooling of the planet drives convection that can kind of erase parts of that gradient. And so it's not clear whether or not the profile that we're seeing is primordial, that is just a product of the formation process, but it might be. And the final thing I'll say is that the excitation mechanism for these modes that I've been talking about and have shown all these incredible results for Saturn's interior is still totally unknown. We don't know why these modes are excited. We don't know what the most important source of dissipation for these modes is. And so the field is really in need of good theoretical ideas for why this might be happening. Some possibilities are forcing by convection. That's what forces P modes in the sun, but it appears to just be too weak for Saturn because of its low luminosity and poor coupling between convective motions and these modes. Giant impacts are one possibility. Moist convective storms are another possibility, and we can talk about those in more detail if anybody likes after the talk. So just to conclude now, because we're about at time or a little past, Saturn's rings have proved to be a sensitive seismograph for planetary oscillations, and they're directly probing composition gradients in a planet for the first time, certainly in a giant planet for the first time. Saturn's core is really a stably stratified gradient extending over more than half the planet's radius, which is a really striking finding that simply is required by these G-mode frequencies that we found in the rings. Is this common in gas giants? We're not totally sure. A final word from Juno, because those gravity orbits are ongoing, might give an indication. If it's true in Jupiter and it's true in Saturn, that it might be true in these gas giants in general, which complicates all of the commonly told stories about their evolution or interior structure based on what we can observe. That's roughly consistent with what's produced by accretion and evolution models, but qualitatively, those models might have trouble producing a core this diffuse. So maybe there's some mixing or other things influencing composition profile after formation while the planet cooled. Ring waves are also providing really important constraints on Saturn's rotation, which is kind of elusive to study by other means. And the process responsible for mode excitation remains totally unknown, which is kind of incredible. The future will really rely on other means of planetary seismology, just because Cassini is finite, because the mission is already over. Wave detections are still being made in the data that is available, but that won't go forever. And so to learn more about the interiors of giant planets, I'm excited about studies of Jupiter from the ground. I think a detection might be kind of imminent from data like that. And also Uranus and Neptune will be really fascinating to study using seismology if that's possible, whether that's using Uranus's rings or orbiters with instrumentation that's dedicated to finding their oscillation modes. I think that could be a game changer for these ice giant planets. So without delaying further, I'll finish and say thank you so much for your attention.
Thank you, Chris. Thank you very much for this wonderful, wonderful talk. Very, very interesting work. And are there questions, comments from the audience? Gloria, you have a question? If you like, you can start.
Yes, thank you. Thank you for this very comprehensive overview and detailed description of the modes. I guess I should have asked this earlier, but I didn't want to interrupt. I'm a stellar astronomer, so for me, measuring P modes and G modes implies that I get a sequence of photometric observations or spectroscopic observations. I understand that in the sun, you have the spatially resolved ability to do spectral and photometric observations. And from there, you are able to deduce the oscillation modes. So my question here is, what is the observable when you are looking at planets such as Jupiter and Saturn?
Oh, that's an excellent question. It depends a little bit about whether we're talking about ring seismology. Ring seismology is pretty, when I say that Saturn's rings are a seismograph, I mean that quite literally. It really is like a seismograph. It's kind of like a physical realization of the spectrum of oscillations, just because frequency is the variable that takes you through the rings, because the resonance condition involves the orbital frequency. The observable, in this case, the observable is the frequency directly. So you're not taking a photometric time series and then finding a power spectrum from that. The rings are showing you the spectrum because the frequency of the mode dictates where it lands spatially in the rings.
So you're just measuring, I mean, you go and you observe the ring and you measure how many wiggles it has or something like that?
Precisely, that's pretty much it. So each one of the detections on this diagram is one of those little plots. If you zoom in by a factor of 1,000 to 10,000, each one of these detections is a little wiggle that is a wave, and its location is a resonance, and that resonance gives you a frequency directly. And right. I should mention that I am not the observer. I am the theorist, but observers like Matt Hedman, Phil Nicholson, and Dick French really did the incredible work that it took to pull out all of these, in many cases, extremely subtle waves out of just stellar occultation data. So those are data that are just probing the ring density as a function of space, and they can extract frequencies and M numbers. Those are the observables for ring seismology.
Okay,
For ground-based Jupiter seismology, it would be akin to what you mentioned for the sun, which is spatially resolved maps of the surface where you can pull out components in different spherical harmonics. And in that case, there's a time series analysis that you need to extract frequencies.
Time series analysis of the brightness or of the spectral features of the profiles of the spectral lines?
Yeah, you can think of it as kind of a hybrid between the two. Have you ever heard of, like, for one example, one kind of instrument you could use to do this is a magneto-optical filter, which is an old technique for making these spatially resolved Doppler maps of the solar surface. And what that is photometry, it's photon counting, but it's in an extremely tiny bandpass near one of the solar absorption lines. And the radial velocities on the surface, because of the pulsations, modulate the light that's coming through that tiny bandpass. Okay. And so from that time series, you can back out a radial velocity map for the surface of the planet as a function of time. And then it's the time series analysis of those radial velocity maps that can give you the power in different angular structures as a function of frequency.
Okay, that's very nice. Thank you so much.
Thank you.
Okay, I think there is another question from Antigona.
Yes, hi. I understand that when these giant planets are formed, they start like falling into themselves, like, and this falling does not stop for billions of years. And I don't know how important is that for these modes of vibrations, and that's one question, and how all this relates to the energy source, because basically I understand that giants emit more energy than the energy that they receive from the sun. And I don't know if this excitation of these vibration modes, it's related to this, or maybe related to the energy source, the internal energy source of these giants.
Right. Yeah, that's an excellent question. And I think the answer is that it might be. It's not totally clear. But yeah, you're right that these planets are constantly undergoing a contraction because they are gradually losing some of their support because they are cooling off. And that cooling drives convection, which is pervasive over whatever parts of the planet are not stabilized by composition gradients. And so contraction and cooling translate to convection. And it's that convection that maybe is the most important source of energy for these modes. But like I mentioned, it's still kind of a challenge. If you just want to explain the amplitudes that these modes appear to have in Saturn by excitation stochastically, by just convective motions, turbulence, the coupling is not really very strong, in part because the dominant time scales of the convection are a lot longer than the fast time scales of these oscillation modes. So it's not easy for the convection and the modes to talk to each other. And so that's kind of the main challenge in just trying to understand the amplitudes in terms of stochastic excitation by convection, driven by cooling, as you say. So that doesn't appear to work perfectly. Maybe there's some other kind of instability related to the fluid dynamics that is really more effective in pumping energy into these modes. And beyond that, I just don't know. We don't know yet.
Okay, thank you very much. There is another question from Miguel Chavez.
Yeah, thank you, Chris. It was a great talk, very comprehensive, and I have to digest part of the material you just presented. My experience with seismology is only a little incursion to seismology of white dwarf stars, and but this is very interesting. And the overall question I have is whether the processes and the analysis you have just presented for Saturn, if they can be applied not only to planets but also to the moons of the giant planets to better understand their interiors.
Thank you, and that's a great question. And given your interest, I have to apologize for referencing solar oscillations and red giant oscillations, but no white dwarf oscillations, because obviously white dwarf pulsations are incredibly interesting kind of phenomenon unto themselves. I do love white dwarfs. I think the answer in short is that these specific methods are very, very unique. Very unique is a silly phrase to use, but I meant it when I said that ring seismology is a unique probe to Saturn, because it has this ring system that is not only substantial, but also has a region that sort of has very intermediate optical depth. And so you can get filtered starlight, that is, light is neither totally blocked nor totally transmitted. And so that lets you back out these measurements of waves. And also have that region be commensurate with the frequency of some of the strong oscillations in the planet. It's very lucky. And the moons of Saturn generally do not have rings. There are a couple tiny bodies in the solar system that do have ring systems. And I think it would be really interesting to pursue seismology of those using their ring systems. But the short answer is that, again, rings are sort of a singularly useful tool. And unfortunately, they don't come easy. And Saturn is kind of rare in its ability to have this really clean ring system that can be used for this kind of science. In general, seismology, of course, can be a useful tool for understanding these things' interiors. But when you talk about small bodies, there is a question of, there's a kind of different question of how these modes are probably excited. The power spectrum might just be kind of dominated by the modes that are able to be forced well by tidal forcing, which puts you in a very different frequency range and can still tell you things about the interior, like love numbers. But it might not get more sophisticated than that. I'm not sure. I hope that it sort of answers your question. Rings make it easy.
Thank you. Thank you, and thanks again for the talk.
Thank you.
Okay, I think there is another question by Gloria.
Yeah, sorry, I just realized. So, are the oscillations in the rings connected to the oscillations of the planet? I thought they were very separate, but somehow no.
Yeah, I'm sorry I didn't make that more clear, but the oscillations in the rings, so some of them I mentioned are because of satellite orbits, but all the ones that are useful for understanding the interior are directly caused by the Saturn oscillations. So the waves, so we're talking about non-radial modes of oscillation inside Saturn. Mm-hmm. And so since they're non-radial modes, they have angular structure. There's also Saturn's rotation on top of that, which carries those structures around the planet in addition to their own intrinsic propagation. And so there are non-axisymmetric gravity perturbations felt outside the planet because of these oscillations. So it's really like effectively there are masses inside the rings moving around. They're actually Saturn oscillations. And it's gravitational influence of those oscillations that give us the waves in the ring. So they're really one and the same. It's the rings picking up this churning in the gravitational field because of the planet's oscillation. So it gives us the planet frequencies directly.
That is amazing. Thank you. That is really nice. I didn't realize that.
To this day, when I sit back and I think about that, I realize just that is an astonishing fact.
Yes, thank you.
Okay, yeah, thank you very much. Are there further questions, comments from the audience? Yeah, if this is not the case, Chris, thank you very much. Thank you very much for this very nice, very interesting talk. And yeah, hope to have you here the next time in person in Cuernavaca. And yeah, to all of you. So too. And to all of you, see you next week. Bye-bye.